Welcome, I'm Scott.
And I'm Joel.
From the Create Energy Center. We're here with an indoor sun setup at Madison Area Technical College today to review how to successfully avoid the pitfalls and take advantage of the opportunities found in our battery storage and charge control lab activity.
Before starting in, here are the student objectives for battery storage and charge control.
1. To understand the function of the charge controller in governing current flow in a renewable energy battery storage system, and
2. To predict, measure, and explain electrical potential, volts, and current, amps, in a variety of dynamic settings.
Here are the primary components we use to carry out battery storage and charge control and why we chose them.
We selected the charge controller, battery, PV module, and the loads we use because they work together well in the system we've designed for this activity. They all feature or are configurable to 12-volt nominal operation.
Our charge controller has very simple and visual inputs and outputs.
The 25-watt PV module we use enables us to charge the battery in a reasonable time frame. The current provided by the PV module enables us to charge the battery during the lesson, allowing students to observe and measure effects on the battery.
Our battery is a 12.8 volt, 8 amp hour lithium iron phosphate or LFP battery. The amp hour capacity of the battery is sufficient to supply the load by itself and is small enough to enable students to observe the effects of the battery discharging within the time frame of the lab.
For most of the lab, the load is a 25-watt, 12-volt incandescent light bulb. We can power the load with the battery or the PV module. It also discharges the battery within the time we expect the activity to take.
In the last lab condition, condition 6, we switched to a 12-volt LED light bulb. It must be a 12-volt LED light bulb.
We use DC-rated circuit breakers in our load center as the switches to connect or isolate the various components of the system. Let's talk about the setup of our board. We've learned that lever connectors for the PV module wires are the simplest for students to use.
We've also found that crimping alligator clips onto the wires for connecting the battery is simple to do and will last a long time. Fork terminals fail after students connect and disconnect them to the battery many times.
The lab begins with the light bulb, the load, not screwed in. This is so students can measure the initial electrical potential supplied to the load on the metal contacts of the lamp holder socket.
When making a board for this lab, we recommend you position the components in the same order as the charge controller terminals and set up the circuit breakers the same way. In other words, we recommend you set up your board to match ours. It will make for a simpler visual presentation to beginning students.
We use 2 multimeters for this lab.
A standard multimeter to measure electrical potential in volts,
and a clamp meter to measure current in amps.
Well, you could do the lab with 1 multimeter. We find that students make fewer errors when we use 2 separate multimeters, each one designated and set up for a specific type of measurement.
To set up the multimeter for the lab, we first place the leads in the proper position. The black lead goes in the black slot, and the red lead goes in the slot marked with a V for volts.
Next, we turn the selector switch to straight line V in order to make a measurement of electrical potential in DC volts.
You may see the meter already indicating millivolt measurements. These are known as ghost voltages and should be ignored.
In the lab, we change leads from alligator to probe style after measuring baseline conditions. Both types of leads are provided with the multimeter we use.
To set up the clamp meter for the lab, we first set the range setting to 2 amps.
The maximum current students will measure in the lab can be determined by using Ohm's law for load current or referring to the nameplate for PV module current.
The default setting for the clamp meter is AC, so we next press the blue select button to change the setting to DC.
Even before placing the meter in position, you may observe some ghost currents in milliamps on the screen of the meter. Press and release the 0 button to get rid of these.
Finally, we place the clamp around one wire to get a current measurement. If we place the clamp around both wires of the circuit, we will not get an accurate measurement.
The charge controller needs to be programmed.
But you'll only ever need to program it once.
First, you'll need to connect a battery to the charge controller to provide it with power. You'll see the charge controller turn on and begin scrolling through measurements.
To program the charge controller for the type of battery we're using, press the Select button to get to the battery voltage screen.
Then press the Enter button for 3 seconds. The battery voltage will be replaced by the word gel. Press the Select button to scroll through the available battery types. When the screen shows Li, press Enter to choose the lithium-ion battery type.
The charge controller screen now shows the nominal battery voltage. The default is 12 volts. Press Enter since this is the nominal voltage of our battery.
Next, the charge controller screen shows 14.2, the setting for the maximum battery voltage the charge controller will permit. Press Enter to accept 14.2.
Li will reappear on the screen. Press Enter for 3 seconds to exit the battery type programming menu.
Now we'll program the mode of operation for the load. The charge controller has load settings that can turn on the load after dark or turn off the load a specific number of hours after the PV module stops supplying power. We want to set the charge controller to keep the load on all the time.
Press the Select button to move to the screen that says Load and the number 15. Press the Enter button for 3 seconds. Press the Select button to scroll through the available options until you reach 17. Press Enter for 3 seconds.
Programming is now complete.
And now, a few lab preparation tips.
To limit the variables students have to manage, the best condition for performing battery storage and charge control is
A sunny day. Variable sunlight conditions result in measurements that may confuse students.
Here at the Create Energy Center, we've developed an indoor sun setup using a stadium LED light suspended from a game hoist tripod.
Your battery should be fully charged before starting the lab. We use the sun to do this. If you use a charger, make sure it's designed to work safely with the battery.
Lithium-ion batteries have an internal battery management system, or BMS.
The BMS for these batteries will put them to sleep to limit self-discharge when they haven't been used in a while. When an electrical potential measurement is made on the sleeping battery, it'll indicate a very low voltage, perhaps less than 1 volt.
However, the battery is not damaged. Applying a charge to the battery from a PV module, for example, We'll reawaken the battery for an accurate electrical potential measurement. In closing, you'll find everything you need to promote your students to a premier experience using this activity at our Create website. Among the educator resources, just look for this lesson, Energy Storage and Charge Control.
In addition to all of the student and instructor resources you'll ever need, is a document listing all of the equipment we use to perform this lab, where we purchased it, and our most recent price update.
You're welcome to edit, alter, revise, and remix any of our educational materials to better suit your setting, your equipment, your students, and your style. But don't get a red card, read our copyright first.
Thank you for watching. We hope we've accomplished our goal of providing you with what you need for a World Cup Championship lab activity.